Hello, welcome, Calculus 1. So moving into section 2.4, I want to talk about continuity. This is a big topic, may take a couple videos. I might do some more examples after this introductory video, but you can look at these pictures. I think it's very clear. Is this function continuous? Is this function continuous? Is this function continuous? And I think the answer is no. I think you see points of discontinuity. But here's a true fact. Polynomials are always continuous, and maybe you know that. Polynomials are continuous for all x. And hopefully you know what a polynomial is. This is a degree 3 cubic polynomial. It's got a few terms, and polynomials are just these beautiful little crazy things. And anyway, they're never undefined, so they don't have holes or asymptotes or breaks. They are continuous. So you start to have discontinuities when you have something that's undefined, and you have something that's undefined usually when you divide by 0. So you have to have some division, and polynomials aren't division of, you don't call those polynomials, you call those rational functions when you have some division of variables. So this definitely has a hole in it, and that's a discontinuity. And what you say is, there's a discontinuity at x equals 2. That's how you talk. You say there's a discontinuity at x equals 3. This one's different. It's a vertical asymptote instead of a hole. We call that a hole. We call that a vertical asymptote. By the way, even if there was a defined part of the function here, it's still a hole. And this function could be defined anywhere. If it happened to be right here, if it was defined there, then I guess all of a sudden it is continuous. But anyway, whether it's defined somewhere or not, that's a hole, that's an asymptote. These are discontinuities. Here's a discontinuity. I don't call that a hole or an asymptote. I call it a break. The function's kind of broken, and it's a discontinuity at x equals 1. Now we do have types of discontinuities, and I'm showing you these types, but there's a word for this. They call them removable or non-removable. That's kind of a funny word, and I think they say that if the function can be redefined to where you could make it continuous, then it's removable. I don't know. The wording in the is a little funny. Here, let me just help you. This hole like this is called removable. This is a removable discontinuity. And sometimes I like to say it's called removable if the limit exists. Now it's a discontinuity because there's a hole, but the limit does exist because both sides line up. So it's a removable discontinuity at x equals 2. But this is a discontinuity at x equals 3. This is a discontinuity at x equals 1. And these are both considered non-removable. And this is a vertical asymptote. It's an undefined place. This hole was an undefined place. But anyway, it's just a little different kind. This is a broken place, so I feel like it's broken. But these are both non-removable discontinuities. Non-removable is the phrase. And I might have some more language. I might have a little bit of other definitions for you. But one way to think of it is these pictures. But another way to think of it is it's non-removable when the limit doesn't exist. So like in this example, the limit does not exist because the left and right don't line up. The limit from the left has an answer. The limit from the right has an answer. This limit also does not exist, and you could also say because the left and the right don't line up. The limit from the left heads toward positive infinity. The limit from the right heads toward negative infinity. But even if they both headed to the same infinity, they're headed toward infinity, and it's an asymptote. We still call it non-removable, and the limit technically doesn't exist, but I might like to know it's headed toward infinity. So anyway, I hope that's not too confusing, but it is a little confusing. New words, new language here. Now listen, so the official definition of continuity is this, and we'll work with this in some problems. So here's the deal. A function f of x is continuous at a point x equals c. So it's not talking about a function being continuous everywhere. It's at a certain point. You're testing a certain point, and you prove it's continuous at that point c if you can pass this three-step definition. So step one is the function is defined at c. So it has to be defined. Step two is the limit has to exist as x approaches c. All right? But then you can pass that test and pass that test, but you still have to pass step three, which is that function value you got from number one and that limit value you got from number two have to be the same. They have to equal each other. So that's the three-step definition. And if you fail one of those steps, then you've proved it's discontinuous at x equals c. It's cool. It's great. It's fun to work with this three-step definition. I like you to be able to write and communicate using this. I'll show you some examples of that. Real quick, let's look over here. Let me put some numbers on here. So like if I was investigating this picture, step one, at x, I'm investigating x equals 2. Okay, let me erase. Hang on, let me officially do this here. And I'm doing it with the picture there. So I'm investigating, and I pretend I don't know it's a discontinuity. So step one, do I have a function value at 2? And there it is. If it's colored in right there, then yes, I do. It's got a function value of 1. The function is defined. All right, step 2 is the limit as x approaches 2. The limit as x approaches 2, does it exist? Well, technically, maybe I should look at the picture, but I should maybe to do this step, you might end up having to investigate the limit from the left and the limit from the right, like in that picture. But in this picture, the limit from the right looks like it's approaching a y value of 3. The limit from the left looks like it's approaching a y value of 3. I think this limit does exist. I think its answer is 3. So far we're passing the test, but hopefully you can see we're about to fail step 3. Step 3 wants this answer to equal this answer, and 1 does not equal 3. So we just failed step 3 of the definition, and that's what made this a discontinuity. Which step does this one fail? And maybe you can tell the limit would not exist. Because of the left and the right not lining up, it would fail step 2. Technically this one fails step 1. Maybe it also fails step 2. But this one fails step 1 because the function's not defined. There is no defined function on an asymptote. So it fails step 1, it's a discontinuity. It also fails step 2. It's a non-removable discontinuity. All right, we'll do more examples. That's a good warm-up there. Thank you for listening.